Triangle ABC is given. Such that C prime, the midpoint of AB, in center and the X touch point of the AX circle with AC produced is Y1. So we'll be using barycentric coordinates for this problem. It's given that angle ABC is 60 degrees and AC is equals to 3. To find AB and BC. So we'll use this usual notations. This is small c, this is small a, this is small b, and r is the radius of the in circle, and s is the semi-perimeter. Barycentric coordinates. So suppose there's a point P in the plane of triangle ABC, and let's call the coordinates of PB x, y, z. So x is defined as area of the triangle PVC, and the orientation of the area is in the anti-clockwise direction upon the area of triangle ABC. Y is defined as PCA, and Z is defined as PAB upon ABC. These are the barycentric coordinates. So the coordinates of A is 1 0 0, B is 0 1 0, C is 0 0 1. Also the midpoint of AB is denoted as CS, C prime. Let it be XYZ. Then X is triangle C prime, area of triangle C prime BC upon ABC. C prime BC upon area, and because CC prime is a median, C prime BC is half the area of ABC. Similarly, y is equals to c prime ca upon abc, which is again half for some reason, and z is c prime ab upon abc, which is 0. So now we would like the coordinates of the in center. And we know that the in circle is tangent to the sides AB, BC and CA. Let the coordinates be x, y, z. Then x is equals to area of IBC upon ABC. This is perpendicular and the in radius is r. So this is half times of RA upon ABC. Now ABC, there is a relation between R and ABC, which is R is equal to triangle by S. So x is equals to half RA upon RS. So this is half A upon S. And S is A plus B plus C plus A plus B plus C by 2, which is A by A plus B plus C. Cyclically, y will be B. Y is equal to B upon A plus B plus C. Z is C upon A plus B plus C. So the coordinates of the in-center are known. And it is given in the problem that for this particular triangle, CI and YI are collinear. So Y1 is the intersection point of AC and CI. So in barycentric coordinates, the equation of a line is also particularly simple. And the equation of a line in barycentric coordinates is ux plus vw vy plus wz equal to 0. So equation of AC, this suppose ux plus vy plus wz equal to 0 is the equation of AC. It passes through A. Whose coordinates are 1, 0, 0. So this means u equal to 0 passes through C, whose coordinates are 0, 0, 1. That means w is equal to 0. So equation is y equals 0. Now equation of CI, ux plus vy plus wz equal to 0 passes through C prime, whose coordinates are half, half, 0. So u by 2 plus v by 2 equal to 0, or we can say u plus v equal to 0. Passes through the in-center, which is a upon a plus b plus c, b upon a plus b plus c, and c upon a plus b plus c. UA, a plus b plus c is the common denominator, so UA plus VB plus WC equal to 0. So these are homogeneous coordinates. So let's just say, and by that I mean the sum of the x, y, and z coordinates of any point are is 1. So we can say u equal to 1. Then from this equation, v is equals to minus 1. So we get a minus b plus wc equals to 0. So w is equals to b minus a upon c. So equation of line c prime I is x minus y plus b minus a upon c, z equal to 0. If we intersect it with AC, whose equation is y equals to 0, we get x plus b minus a upon c, z equals to 0. So z is equals to minus x or cx upon a minus b. So these are the coordinates. The coordinates of y1 are thus x 0 cx upon a minus b, and because the sum of these coordinates are 1 is 1, so it's x plus 0 plus cx upon a minus b is equals to 1. We would like to know what the value of x is. What is the value of x? Ax minus bx plus cx is equals to a minus b. X is equals to a minus b upon a minus b plus c. So y1 is a minus b upon a minus b plus c, 0, c times of a minus b plus c. So another property of y1 that I1 y1 is perpendicular to AC, because this is where this x circle touches and is a tangent, and I1 is the center of the x center. So I1 y1 is perpendicular to AC. So in the barycentric coordinates, there is another perpendicularity condition which we can express in terms of these coordinates. So let us work through that. If P is if the normalized coordinates of P is x1, y1, z1, and that of Q is x2, y2, z2, then the displacement vector PQ is defined as x2 minus x1, y2 minus y1, z2 minus z1. Over here, these are not the barycentric coordinates. This is just a way to represent this vector pq. So sum of these coordinates is not 1, rather it's 0. So pq vector is a vector in the plane of triangle AC, is a vector in the plane of the triangle ABC. And if the plane is such that the origin of the plane, the vector plane, the origin of the vector plane coincides with the circumcenter of the triangle ABC, so then this can be written as A vector, and this is B vector, and this is C vector. And any vector in the plane can be written as sum of two non-parallel vectors, or it can be written as sum of these three vectors. But then suppose a vector pq is written as what in linear algebra we say that these vectors are not linearly independent, because in a plane, for example, we have I vector, j vector. Any vector can be written in terms of I vector and as a linear combination of I hat and j hat, where I hat and j hat are the unit vectors, perpendicular unit vectors. They need not be perpendicular. Any two vectors will do over here. So, but now we are saying that we can also write in terms of these three vectors. So there is an additional condition. So there is an additional condition. An additional condition has to be imposed on these three numbers x, y, and z, if we so choose to write pq. If we let x, y, z to be such that x plus y plus z is equal to 0, then we have got a representation of pq in terms of as a linear combination of a vector, b vector, and c vector. But these x, y, z are then these three numbers. So suppose displacement vector pq is x1, y1, z1, and mn x2, y2, z2. So pq will be perpendicular to mn if and only if this representation of pq vector and mn vector are perpendicular. So two vectors are perpendicular if the dot product is 0. Which is true if, so we'll just expand this, x1, x2, a vector dot a vector summation plus x1, y2 plus x2, y1. A dot v vector is same as b dot a vector summation. Now, in that triangle, because the origin is at the circumcenter. This is A vector, this is B vector. So A dot A vector is equals to mod of A vector square. Absolute value, norm of this vector, length of this vector, square of the length of this vector, because the angle between them is 0 and cos of 0 is 1, and this is equal to the circumradius. And this angle if this is angle A, then this is also angle A, and this is also angle A. So angle BOC is twice of angle A, because angle subtended at the center is twice the angle subtended on the circle. So angle between OA vector and OB vector is 2C, 2 angle C. A vector so A vector dot B vector is length of vector A, length of vector B, cos of 2C, which is R square cos of 2C. So we have to get rid of 2C here. So we'll use the cosine rule in the triangle OAB. So OA square plus OB square and this is C. So C square is equals to OA square plus OB square minus 2 OA OB cos of angle 2C. C square is equal to R square plus R square minus 2 square cos of 2C. 2 square cos of 2C is 2R square minus C square. R square cos of 2C, R square minus C square by 2. So A vector dot B vector is R square minus C square by 2. So let us write this again. Summation of x1 x2 r square plus summation of x1 y2 plus x2 y1 r square minus c square by 2 0. Summation of x1 x2 plus summation of x1 y2 r square summation of x1 y2 plus x2 y1 c square y2. This is just the product of x1 plus y1 plus z1 with x2 plus y2 plus z2. And This is equals to 0, this is equal to 0. So it is summation of x1 y2 summation of x2 y1 c square. So this is the perpendicularity condition. Perpendicularity condition. So we would need the coordinates of I1 also. So you know I1 y1 is perpendicular to AC. Coordinates of A and C are known, so the displacement vector AC vector is known. Let that be called x2 y2 z2. And coordinates of y1 is known. Coordinate of I1 is actually very similar to coordinate of I, and it can be derived in a similar way. So taking care of the orientation of the triangles, I'll just write the result here. So I1 is minus A upon minus A plus B plus C, B upon minus A plus B plus C, and C upon minus A plus B plus C. And y1 was obtained earlier as this. So displacement vector I1 y1 can be obtained by subtracting these two. Let's call it x1 y1 z1. So using this perpendicularity condition, where x1 y1 z1 are these and x2 y2 z2 are these for AC, we'll get a relation between A, B and C. It's called relation 1, perpendicularity condition. Then in the triangle ABC is given that angle B is 60 degrees and C is, so B square is equals to A square plus C square minus 2AC cos of 60 degrees. A square plus C square minus AC. Let's call it condition 2, the cosine rho. And also it's given that B is equals to 3. So there are three equations, three non-linear equations, and they can be solved and using it does get slightly messy over here, FABC. So the answer is A is root 6 plus 1 and B is equal to 2, or so C is equal to 2 or root 6 minus 1.